Department of Civil Engineering. So I welcome you all to this online series, Research Scope in Emerging Areas of Civil Engineering, which is organized by Aditya Learning Academy in association with Department of Civil Engineering. So as part of the day 5 content, so my lecture series is going like the topic called fluvial hydrodynamics around parallel bridge piers. So to understand the fluvial hydrodynamics, so we need to the the basic understanding is like two courses are required. One is the fluid mechanics and another one is open channel hydraulics. So without understanding of these two courses, the topic of fluid hydrodynamics is not understand. So my sincere request is after hearing this lecture, so once again you can go through it by completing the courses of the fluid mechanics and as well as the open channel hydraulics. Next, so to understand the fluid hydrodynamics, so we require some fundamental concepts like streamlines, path line, boundary layer, vorticity, circulation, and some turbulence parameters. So with after then I will cover some research point of view how all these hydrodynamics has been covered in the research point of view. Now, so let us understand each and everything. So firstly, I will define what is meant by the fluid hydrodynamics. Fluid hydrodynamics is it is a fluvial process in a river like aggradation, degradation, local scour. So many geological formations has been occurring. So in the today's lecture, I will cover only one of the geological formation called the local scour around the bridge pier. So that is one of the fluid hydrodynamics I would like to cover. So to understand that, I will start with streamline pattern. So now, what is meant by streamline? Of course, streamline is a imaginary line where we can't see with our naked eye. But if we draw a tangent at any point in the fluid flow, it will give the direction. It means, for example, as a streamline is a vector quantity. So as a vector means it will give both magnitude as well as the direction. So if you touch the fluid flow at any point, or if you draw the tangent at any point in the fluid flow, it will give direction of the velocity and as well as magnitude of that velocity. So that is the main representation of the streamline. So the definition you can see on the screen, it is a curve that is everywhere tangent to the instantaneous local velocity vector. It means it will give the instantaneous velocity. In the layman language, I can say, if you take the photograph of a, of a fluid, flowing fluid, that image itself showing all the streamlines. So at that instant, what is the velocity of that particular fluid particle? What is its direction? That is what the streamline is indicating. Next, path line. Path line is completely a different concept, but it is a scalar quantity. So with the help of the path line, we can know only location of a particular fluid particle. It means, for example, student A, he wake up at 6 o'clock in his room. At 7 o'clock, he is in bathroom. At 9 o'clock, he, uh, maybe he's in canteen. At 10 o'clock, he's in college. At 12 o'clock, he's in movie theater. At 11 o'clock, again at 6 o'clock, he's in the campus. Again, 12 o'clock, he's in his room. So if you add all these points, that line is nothing but a path line. It means from the path line, we can identify, we can trace out that particular fluid particle. So with the help of the path line, we can identify where the particular fluid particle is. So that is the advantage of the fluid particle. But at a different instance, it will give. So as a conclusion, the streamline will give direction and as well as the velocity of different fluid particles at that instant. At the same time, the path line will give location at different time intervals. Next, so vorticity and circulation. Yeah. So to understand the vorticity, we should, of course, the vorticity means is nothing but a circulation of a particular fluid particle, means rotation, the local rotation of a fluid particle. It means to understand the local rotation, we should know the concept of the angular velocity. So what is meant by angular velocity then? Angular velocity is it is a average rate of rotation of two fluid particles perpendicular to each other at the same point. It means it will give angular velocity omega x is equal to so du by dy minus du by dx, like that. So if we add in all three directions, it will give the angular velocity vector. So if you double that angular velocity vector, that will give the vorticity. So vorticity is nothing but 2 times of the angular velocity vector. So in simple mathematical term, if I say vorticity means divergence of the velocity vector. If I have the velocity field, simply I can compute the vorticity, right? So mathematically, uh, how it represents, we can see on the screen, dw bar by dy minus dv by dz and so on in the equation 2.1. And now from now what is meant by circulation? So circulation means it is a line integral of a velocity vector again. So in a closed curve. So so the main advantage of the circulation is we can quantify the vorticity, means how many rotations in a particular instant we can give by the circulation. So the circulation will inform that these many rotations are occurred. So that is what it will quantify particular fluid particle. Next, how to compute the circulation again with the help of the vorticity. So we can't compute directly. We have to apply Stokes theorem. Stokes theorem will help to convert the line integral to surface integral. The moment it will convert to surface integral, if we multiply with area with the vorticity, it will get the circulation. So in a conclusion, I can say in general, the circulation is a line integral of the velocity field, and vorticity is the circulation per unit area. So that is what we need to understand. Next, next concept is the boundary layer. So on the screen, you can see the boundary layer means if you see in the left side image, so one thick line will be there on the plate. So when the flow is approaching to a thin plate, we can see one solid line. So that is nothing but the boundary layer. Means what exactly it is? Actual boundary layer is a very thin layer which is close to our body itself. Everywhere it is there. So below the boundary layer, the velocity gradient is existing. What is velocity gradient? Du by dy. Du by dy means with respect to depth, how the velocity is varying. That is called the velocity gradient. If the velocity gradient is existing, means du by dy is not equal to 0. In that case, the boundary layer will exist. Above the boundary layer, du by dy is 0. It means approaching free stream velocity, let us say u infinity, will be constant at all the water levels above the boundary layer. So, so below the boundary layer, velocity gradient will exist. Above the boundary layer, velocity gradient is not existing. So, if the velocity gradient is existing means, so tau is also existing. Tau means shear stress. So, below the boundary layer, we can have rotational flow. On the other hand, above the boundary layer, we have irrotational flow. So that is what the understanding from the boundary layer concept. Now, what is meant by boundary layer separation then? So boundary layer separation, to understand the boundary layer separation, just see the below image. There is a ball which is completely inside a fluid region. So above and below, we can see a lines called the streamlines. Very nearer to the ball, one small layer is there. That is nothing but the boundary layer. When the fluid is touching to this ball, uh, we can have a stagnation point. After some time, another stagnation points also we can see on the screen. See, what is meant the stagnation point? The moment the velocity becomes zero, when the fluid touches to any boundary, the velocity is drastically touching to zero. So that is nothing but the stagnation point. Now, after velocity is reduced to zero, our pressure is drastically, significantly increased. So now it is high pressure zone. Now always the fluid move from high pressure to low pressure naturally. So it will divert to the side and it reach to low pressure region. Okay, fine. Now again it will reach to low pressure to high pressure region. Then the problem will occur for the fluid particles. There the fluid particles don't have enough energy. So it the particles nearer to the boundary don't have enough time. So it need to separate the boundary when the fluid flow from low pressure to high pressure zone. So that's why behind the car or behind the any ball we can have eddies or vortices we can observe naturally. So that region is known as wake region. The point where it is separating is nothing but the boundary layer separation. On the screen left right side we can see the velocity vectors, velocity profiles. So starting profile, a second profile. So from the second profile everything is fine. The moment it reached to the low pressure region, so the reverse flow has been started, means there the boundary layer has been separating. So this is what the understanding of the boundary layer concept, right? See, and also we in the boundary layer so many are there: laminar boundary layer, turbulent boundary layers, so many things are there. I will give one small example. What is the difference between laminar and turbulent? If we have a glass of milk, just added a sugar, and if you drink, that is nothing but the laminar boundary layer. If we mix and drink, then that is a turbulent boundary layer. So turbulence will help you enhance. So in the second case, because of this mixing, the sweet has been entered to all the fluid particles and we are enjoying the dish. So in the lively, we can have the turbulent. Uh, the turbulence is very much important in many cases. Of course, there are so many disadvantages are there, but so these are the few advantages among the uh, turbulent boundary layer. So yeah, so these are the some basic terminologies we should understand to understand the fluid hydrodynamics. Now coming to the research point of view, um, so as I told before, so many geological formations are there. Among that, I am choosing local scour. So to understand that local scour on the screen, I kept two images. In the right side image, you can see there is a bridge, and below there are three supports are there. So if you see the three supports, the middle support is nothing but the pier, and end supports are abutments. So that is the terminology we will use the bridge. So if you see there is a bed level has been lowered in the due course of time. The dotted line will saying that original bed level, and after so many years or so many months the bed level has been increased, means lowered. So why it is? Due to the erosion action of the fluid. So that lowering of the bed level near vicinity of any hydraulic structure is nothing but the local scour. So scour means it's a pit. So the pit has been created around the structure. Simple. So if you see the definition, scour is a natural phenomenon, of course. It's a lowering the level of the riverbed by erosion action of the flowing stream. So how much amount of uh, the bed has been leveled down? So the original to till. So that difference is nothing but the scour depth. So in the left side image showing the flow physics, what happened exactly, the local score occurred. So many the boundary layer concepts, vortex, streamline, so many things are happened around the hydraulic structure. If you see, as and when the flow is obstructed by any hydraulic structure, say bridge pier, as I told, when it touches to structure, it will reach to stagnation, means the velocity is drastically reduced. Now it reaches to downflow. The moment the downflow is created, then it will leads to a primary vortex, because the approaching fluid particles are pushing. So already the down particles need to circulate. So there is no option. They need to circulate. So that rotation is nothing but the primary vortex. And later it will separate and went to behind the pier. And behind we can see reverse flow, wave vortex. In the upcoming slides, I will show all those images. So complete flow physics, you people can understand by today's lecture. Yeah. Now, briefly, I will go to only 2 to 3 literature reviews. What exactly the people are doing in the world is Astayani. These are the Iranian research scholars. They did the local score around single pair and as well as the tandem pairs. So tandem means in the B you can see that is the position of the tandem pair. So they kept at a 3 times of diameter center to center and studied what happening exactly local score. So if you see uh, in the tandem case, they observed that the downstream pair 50% of the local score has been reduced because of the sheltering effect of the upstream pair. So that is what they explained in the literature. Of course, not only experimentation, they did so many numerical simulations and you know many many parameters has been computed. From all those things, they decided that downstream peer has been very much safe in tandem case because local score has been reduced by 50%. So that is what the study from the Astian Kodakandi. And Vijayashri, she from IIT Bombay, she did uh, different shapes, circular shape, how much local score, triangle, trapezoidal, oblong shape. So many things she did. In all the cases, she observed that oblong shape means on the screen you can see oblong shape. That is the best shape where the low flow separation, low local score, everything has been low. So this is one of the good study in the recent. So oblong shape is the very much application oriented shape. So that's why if you see any bridges while traveling through train, you can see many bridge piers are looking like oblong shape, not circular or rectangle or trapezoidal. So oblong is the very famous shape. So we can reduce the turbulence and reduce the flow separation. So the boundary layer separation is very important. So where we are having less boundary layer separation, there we can have less score. So that is what the understanding is. Yeah, the main motivation of the study is, so due to the rapid urbanization and increasing population, we can have there is a necessity to construct upstream bridge or downstream bridge with respect to existing bridge. So definitely there is a need because all the bridges are very old, but traffic is increasing. So we need to construct definitely. So now at what spacing we have to go, and whether the upstream bridge or downstream bridge, in what arrangement the pier should be, whether it should be tandem or staggered or which alignment. So my research is completely uh, in this area only. So I need to construct a new bridge with respect to the existing one. Now the new pier should be either tandem position or staggered position. If it is staggered, at what degree? So all these things I played in my research. So ultimate aim is to provide the smooth functioning of the traffic and reduce the accidents. So that is what the main motivation of the research. See, to fulfill this objective, uh, we have experimental setup in my institute, SPNIT. So we have a recirculating sediment transport flume, which is the length of a 15 meter, width of 0.89 meter, and a 0.6 meter depth. So these are the dimensions of the flume. It is a 2 crore instrument. So this is completely controlled by the SCADA system. Means no need to touch any valve. If I want, uh, let us say 50 lps in my working station, simply I entered 50 lps. After some time, it will directly release that water into the working station. So that much sophisticated system has been developed uh, to experimentations in our institute. So we can see on the screen there is elevation and plan of this experimental setup. So we have a 6 meter long experimental setup. uh, Initially we covered with the big boulders to develop the flow, and small size and again small size, then the sediment bed has been kept, and in that sediment bed my bridge piers will be there. So this is what the schematic of experimental setup, and these are the arrangements of the piers. On the screen you can see three pier arrangements. One is A, which is a isolated case in single. B is a tandem case. I'm sorry. B is the tandem case, which is separated by the two times of the diameter, and C is the staggered case, two upstream and one downstream. So the downstream pier is exactly located in the center line of this at a distance of two times of the diameter. So in these three arrangements I did in my research. So till now the tandem only people are did, but staggered are very scarce in literature. So I uh, focused on the staggered very much. So so in these arrangements, so these are the different grids which we need to develop first, where we need to collect the data. Here in the open channel, to compute the local scour and turbulence, we required two data sets here. One is ADV, velocity signals, another one is bed elevations. So to detect the velocity signals, we have acoustic Doppler velocity meter, which is called ADV. Second one is ultrasonic ranging system, which is URS, which detect the bed elevations. So these are the two instruments I used. The ADV is around a cost of 70 lakh, and ultrasonic ranging system is around 35 to 40 lakh. So these are the two instrument are there available already in my institute, so that I carry my experiments very smoothly. So if you see on the screen, these are the different grid points, single, tandem, and staggered at different locations where I need to collect all the signals. And yeah, this is the schematic arrangement of the ultrasonic ranging system transducers where I collected. I will show some video also, uh, how I collected, how the instrument looking like, all those things. And this is the uh, data collection with ADV. ADV is a very hi-fi instrument which is having total four sensors. One is receiving and three are detected. So you can see on the screen. So three are receiving a velocity and one is sending a signal. So it is working at a maximum of the 50 frequency hertz. Means in 1 second I can collect 50 samples, means 50 velocity data instantaneously. The advantage of this ADV is, for a particular fluid particle, it will sense or it will detect not only x direction velocity, it will give y direction as well as z direction velocity also. So that is the main advantage of this ADV. So on other hand, ultrasonic ranging also will give the instantaneous bed elevation only. At that instant elevation, what is the bed level? So uh, I will show a small video, um, how the ADV has been collected during my experimentations. Let me play this. Just have a look how the my bridge peers are there, and how the flume. I will. It's loading. Yeah, these are the staggered arrangement experimentation. So this is the ADV, which is near how I collected the data. Uh, I'm showing one sample video here. Three probes will detecting three directional velocities. The center one will sending a signal. This is the rigid bed experiment. Means there is no sediment particles in the flume. This is how looking like the staggered arrangement is. So left to right is the flow direction. Yeah, this is about ADV data collection sample video, and in the same way, I can show you how the ultrasonic ranging is looking like, because these are the two instrument I have been used during my entire research. This is the transducer's plate, and 32 transducers has been inserted over the bridge piers. This is how the data collection has been taken. So 32 sensors are collecting without any delay. So this is one of the mobile bed case. So these are the arrangement at there in our institute. This is the working area. This is the setup there. So yeah, this is what yes. So yeah, now after after collection of both the data sets, the main important task is here, the challenging task is we need to process the data. In case of ultrasonic ranging system, there is no need to process the data, we can use directly as it is. But in case of acoustic Doppler, it will get so much of noise. It means it not only detect the velocity signal, it also detect uh, you know unwanted signals. So many unwanted signals also detected in the uh, instantaneous velocities. So the velocities, ultimately in the Excel sheet we can see all the numbers. We feel that all are the velocity signals only, but in between some wrong signals also there, that we need to clean it. If we didn't cleaning directly, doing analysis is very bad thing. So this is what the literature said, that we have to process the ADV data first, then only we can do the further analysis. So to do processing, I taken almost 8 8 to 9 months understanding of this cleaning a data set, because so much coding, a MATLAB, everything need to understand during this process. Because if you have instrument, uh, if it is getting the data, doing analysis, that is very easy. But data, after data collection, the important step here is the processing is very important. In my case, it may be not for all the cases, but in my case, I'm using ADV, so I have to process it. So my with my fellow scholars, I sit together during nights 3 to 4 months, and with EC Scholar, I think EC Scholar helped me a lot during developing of MATLAB code, and he learned me everything. So finally, we created one code, how to clean the unwanted signals for a given data set. So after successfully generated that code, and I ran in the MATLAB, and these are some screenshots. A, B, C are there. A means that is a raw signal data, exactly how it is looking like. Means with respect to time, how the signals has been generated. In the B case, somewhat cleaned. In the layman language, I'm saying in the B case, it is interpolated only just because some portion has been cleaned. In the C, completely clean data set. So there is so many steps involved in this uh, cleaning process. So there are so many steps. So cleaning, interpolation, despiking, and again interpolation. So many things we need to do. All those things. The final step is the C, which is a completely clean data set, so we can go for further analysis, right? Now now the main important step here is, uh, yeah, I develop my own code and I run. Okay, fine, but how to quantify that my code is correct? So the scientists are very intelligent. They already created some set of norms. If anybody did like this codes, so they need to check with this scale. So the processed data, I need to check with this Kolmogorov scale. Kolmogorov scale means in the turbulence, there are three ranges are there. One is energy production, next one is inertial subrange, and third one is the dissipation range. It means energy is created, then maintained, and after that it is dissipated. So, so in the inertial subrange, so so production and inertial is okay. So in the inertial subrange, uh, the slope of that graph should be minus 5 by 3. If it is not following that minus 5 by 3, whatever I developed, the code processed, everything is wrong. So we have to prove that inertial subrange slope should be minus 5 by 3. So that is the validation part. With the help of this Kolmogorov scale, I validated with inertial subrange is having a slope of minus 5 by 3, and I communicated with a journal also, ISA Journal of Hydraulic Engineering. So, okay, so let us take a small break. So, due to some technical issue, the last slide, the I'm unable to show to this audience. So, once again, I'm sharing this post processing of ADV data screen. See, in this screen, we can see three images are there: A, B, C. A is the, yeah, A we can say is a raw signal data. A is the raw signal data, and B and C are almost processed, but C is completely cleaned data set. So after post processing the ADV signals, we need to yeah, we need to check our processor data with the Kolmogorov scale. So where we can have the inertial subrange, uh, the slope of minus 5 by 3. So as I told earlier, in the turbulence, we are having three regions are there. One is energy production range, inertial subrange, and energy dissipation range. Means energy is created, maintained, and dissipated. So energy production is okay. In the inertial subrange, the data should have the slope of -5/3. So this is the validation for our open channel flow velocity data if we collected with ADV. So this is what the scientist has been set in the long years back itself. So our code which we developed, um, whether it is true or not, this is the only validation. So I validated with, and also I communicated with a journal. It is the worldwide accepted. So I safely do my further analysis. Yeah. Now, of course, this is called a law of wall. Means in the open channel flow, one more concept is a logarithmic nature. I tell the boundary layer should be logarithmic nature. So if it is logarithmic nature, then only we can the flow will be developed. Unless until our flow is not developed in our working area, we can't do any experiments. So the flow should develop in our working area. Means all the uniform flow study, unstudy, everything will be clearly um, classified or clearly explained in the developed flow region only, not the undeveloped region. So 1 meter upstream to my pier, I taken velocity data along the depth across the three sections, and I plotted and I compared with the theoretical profile. So luckily it matched uh, in both the rigid and mobile bed cases. So successfully the flow is also developed. So now as a conclusion, ADV data, ultrasonic ranging, I mean bed elevation data has been collected, it's processed, and it's validated with Kolmogorov scale, and it also checked that flow is developed. So these are the different steps has been cross-checked while going for further analysis. So now I can start my exact analysis. So the first analysis I do is the streamline patterns. So on the screen you can see the streamlines. See how carefully observe about the streamline here, upstream of the pier and downstream of the pier, how the flow pattern, how the flow visualization is. So this is the very important character or very important parameter where the authors or where the scientists can understand how the flow is, how the fluid particles is moving around the any structure. So from this diagram, above is the rigid bed case. Means rigid bed means there is no sediment particle, completely rigid case. Simply I stick the pier. So that's why there is no hole we can't see. But I can study the flow physics. And below is the mobile bed case. So there is a sediment particles are there. So that's why we can have a scour hole. So in the both cases, there is a downflow created, then it leads to a primary vortex has been generated, and at the downstream side we can see some flow reversal, and then again the mainstream region. So these complete fluid hydrodynamics we can see in the streamlines itself. So streamlines are very very important. Sorry, streamlines are the main important step for any further analysis. So with this visualization we can know where exactly the stagnation point is, where the boundary layer has been separated. So we can see the boundary layer separated at around 1.5 to 2. So there I can see the separation. So like this. So these are the some fundamentals will help us to understand actual flow physics. Yeah, these are the streamline patterns, and of course, I as the streamlines will give both velocity and as well as direction. I already using the velocity here, so I can see only the direction here. But yeah, this is nothing but a primary vortex which I can see on the screen, and these Before case is the single pair case, and this is the tandem pair case. In the pair case, we recognized that we observed one recirculation zone has been generated. So means because of this regenerated recirculation zone, the velocity has been significantly reduced. So this is why the region, uh, the local score in the downstream pair has been reduced. So because of this recirculation zone, the particles are the flow, the fluid particles are moving very slowly, so it is unable to erode the bed particles. So there is no local sour is happening behind the pier, means a downstream pier. And in the case of the staggered case, we can see the same scenario as isolated case, but the size of the vortex has been magnified. We can see on the rigid bed case, the size of the vortex has been seen very big size. So it means there is a tendency to detect or erode more amount of the sediment bed. So these are the vector fields I drawn. Same streamlines and vector fields almost same, but in the streamline I can see only the direction, but in the vector field, direction and as well as the magnitude also I can see. Means how I can see the magnitude means, if the arrow is very small, it means the velocity is small. The size of the vector is s- large, means the velocity is high. So that is what the understanding of the vector. So the primary vertex in case of the isolated case, recirculation zone in case of a tandem case, large size of the primary vertex again in the staggered case. So these are the three different type of scientific observations has been worked through the vector fields. Then yeah, vorticity. So these are the contour maps which I plotted using the velocity field. um, A, B, C, D represents at in front of the pier, means A single pier, B tandem front pair, C staggered front pair, D is a staggered rear pair. How the vorticity contours are on the same line, A1, B1, C1, D1 are the 90° to the flow direction. So in the A, B, C, D, we can see the C is the staggered case. So in the staggered front pair, I can have maximum vorticity has been observed. See, one hidden information we can see from this plots is the red color is the primary vortex, already we seen in the streamline. But after plotting these verticity fields, I come to know that there is another vortex which is known as secondary vortex has been beneath the primary vortex, that is known as secondary vortex. In the literature, the combination of primary and secondary vortex is known as the horseshoe vortex. So that is the main hero to erode the sediment bed particles around any hydraulic structure. So horseshoe vortex is the main thing which can erode the particles from the mobile bed. So that we can see both the vortices in case of the vorticity fields. So yeah, similarly in the mobile bed case, how the contours has been seen. So again, if you see uh, the staggered front pair case, again getting maximum uh, vorticity strength. So now these are the circulations I have been computed. So of course, as I told, the circulation means with the quantification of the vorticity will be taken care by the circulation only. I'm sorry. The in the both rigid and mobile bed cases, I'm getting maximum in staggered case only. It means what it is saying is more amount of erosion, more amount of deposition has been occurring in staggered case compared to tandem. So this is what the understanding, because large numbers has been seen in the staggered case, which are highlighted with red color. So these are the circulation, and of course after the basic dynamics has been completed, now it is part to study that how the turbulence is. So in the turbulence, main three parameters are there. One is turbulence intensity, turbulence kinetic energy, and Reynolds shear stresses or bed shear stresses. So these three are very, very important to understand how the turbulence is. So so basically, what is the intensity? Means turbulence intensity. See, turbulence intensity is uh, it is how much the velocity has been fluctuated with respect to the mean velocity. If more fluctuation is there, more intensity. If more fluctuation means more intensity. Means fluctuation should be very less for the safest case. If fluctuations are more, it means it leads to more erosion or more amount of particles has been removing, so it will move staggered manner and it will do very big nonsense. So fluctuations should be less in such a way that it should be low intensity. For example, uh, to fly a flight at high altitude, the intensity should be less. So then only the people will not feel high turbulence. If intensity is high, then they will feel more turbulence inside. So the turbulence intensity is also calculated, and I observed that in the staggered case, I'm getting maximum intensity. So we can see on the screen it is highlighted. And turbulent kinetic energy, it means in the fluctuations how much energy are present in that fluctuation components. So that energy is nothing but the turbulent kinetic energy. Both are interrelated. Turbulent intensity and kinetic energy both are interrelated. So intensity is only saying that okay, it's very dangerous, how much energy it is. So that quantification or that magnitude will be held by the kinetic energy only. So this much turbulence has been present, this much energy has been generated, that I can see on the uh, staggered case. So the staggered case is saying that more amount of turbulent kinetic energy. So uh, now again the bed shear stresses. So bed shear stresses is a simple analysis. We can plot in Excel sheet itself. Uh, Wherever more bed shear stress, there more bed erosion means more cover is. So that is what the meaning is. In the A, we can see in front of the pier, exactly it reads to equilibrium condition. That's why it all the single, tandem and staggered cases are merged to one. So it means it reached to equilibrium condition, particles are verge of motion. So that is the meaning of the equilibrium condition. In the B case, means at 90-degree means side, little bit particles are moving. So that is what the meaning. But behind the piers, we can see more number of sediment particles are moving. So what the understanding from the bed shear stresses are, the movement of the particles are very, very high in the behind the piers, not in front. If you see, the local score has been occurred after, if the river is dry around the pier, if you see in front, compared to in front, backside we can see very big hole. So that is the why, because is because of the bed shear stresses. So bed shear stresses will clearly indicating that at behind the piers we can have maximum uh, transport of the sediments. Yeah. So these are the things I'm saying already. For the single pair case how it is, an isolated case how it is, a tandem case how it is. So this is what the meaning is. And one more analysis I did is power spectra analysis. Power spectra means it is what is the strength of the vortex. Of course, circulation also saying the same thing, but it is giving only the number, but how to show in a graphical way. So to show in a graphical way, we have a tool called power spectral analysis. The spectral analysis will tell what is the strength of the vortex around the peer. So on the screen we can see above is the isolated peer and below is the tandem peer case. In the isolated peer case, the blue color is the x direction velocity, red color is the v direction, means y direction, means transfer direction velocity, yellow color is the vertical direction. Upstream, of course, u direction velocity is high, but behind, if you see, red color is getting a significant peak, means transversal motion of the particles are identified. So this we can see in the power spectral analysis. Means if let us say this is the peer, uh, so this is the peer, this is the flow direction. So upstream we can have u velocities are high, but in the downstream the transverse velocity is getting very high. Means there is a three-dimensional nature. In the 2D plane we can see how the velocities has been playing. So in the tandem case, in between pairs, upstream, downstream, everything we can see only the V component, means transversal component is the significant component compared to U. So we can see in the wake region, the transversal component getting the maximum intensity or strength of the vertex is very high. So compared to rigid bed, staggered case, so many spikes we can see. It means around the piers upstream or downstream, we are getting maximum strength. The vertex is having highest strength compared to previous cases of staggered, tandem, and isolated. And this I communicated with the International Journal of Civil Engineering, which is accepted. The vorticity and strength of the vortex is very high. So the people are accepted that staggered getting highest strength of the vortex. So the same thing I computed on the mobile bed case. Of course, because of the sediment particle, the flow has been reduced and the velocity also reduced. Because of that velocity reduction, spikes and all we are not getting very much intense compared to a rigid bed. In the mobile bed, we are getting less spikes. So these are the three-dimensional scour hole patterns. How the scour hole has been generated. So these are the contour maps of the scour hole pattern of both tandem and the staggered cases. So we can see clearly in the staggered case, upstream piers having mm, maximum scout depth. So compared to the tandem cases, we can see with our eye also. So this is what the understanding from the three-dimensional scour hole pattern. Next, some space-time analysis also we have been carried. How with respect to time at a t is equal to 5. So these are the ultrasonic ranging analysis with the bed elevation data. How what are the things I'm carrying? That's what I'm showing here. So the bed elevations, how with respect to time, means at t is equal to 0, how the bed particles are there at t is equal to 5 minutes, 15 minutes, 120 minutes, 2 hour, 3 hour, up to 6 hour, how the particles are moving around the pier has been shown in case of the uh, single, tandem, and isolated staggered cases. So from these space-time analysis, staggered case is showing maximum scout depth. So this is what the observation from the space-time dynamics, and these are the equilibrium scour hole, because these are the compulsory plot. Those who are doing experiments in the local scour, whether it is getting equilibrium or not after certain time. So it is observed that for the single peer case, it is getting after 3 hours. The equilibrium means after 3 hours there is no sediment motion around the hydraulic structure. And in the tandem case, it is getting almost I think 5 hours. But in the staggered case, it reached up to 6 to 7 hours. So this is what the time frames for all the three arrangements. Yeah, these are the comparison of the bed elevation and the velocity. So these are the contour maps which I can show where we are getting maximum velocity. There bed elevations are very very high. So this is what the observation from this contour maps. So uh, it, we can see ABC. So C is the staggered peer case. So there the velocities are very very high, and of course the bed elevations are very very high. So it leads to more scour around that. So these are the real time images during the experimentation how the scour hole has been created around the three arrangements, and respective bed gradients has been shown in the contour maps. So yeah, up up to all this analysis, so these are the my broad conclusions I can say. uh, from the vorticity and circulation, I can say staggered case getting maximum strength of the vortex are very very high in case of the staggered case compared to tandem and isolated case. So it is observed 30% strengths are increased in staggered case, and also intensities and turbulent kinetic energy also saying that same 30 to 40% intensities are observed very very high in in staggered case compared to tandem. And Reynolds shear stresses and power spectral analysis also the saying same. It is saying that 50% of the shear stresses has been decreased in the tandem case. On the other hand, 30% of the shear stresses are increased in the staggered case. So spectral analysis also revealed the same. The strength of the vertex in the wake and as well as in front getting very very significant in the case of the staggered case compared to tandem and isolated. So on a single stretch, I can say that. So if you construct a bridge upstream or downstream compared to with respect to existing, always we can go for only tandem case. Don't go for staggered case because my experiments are. I can give a suggestion to the hydraulic engineer that if you construct a new bridge, go in a tandem alignment. Don't go for staggered arrangement. So staggered arrangement will lead local score more, and it leads to failure of the bridge in the due course of time. So these are the things. So during my research, I have been communicated 7 journals and 7 international conferences and 3 book chapters has been done during my research. So I went to uh, Kuala Lumpur to present one of the international research. I have so much interaction there, and with the help of that visit itself, I get many contacts. So it helped me a lot. So my suggestion is uh, we should roam, then only we can get some idea. So sitting one place ideally is not good. So we roam and have touch with all the groups, and so these are the scope for the future work. So with respect to my work, so these are the, if anybody want to do research in this fluid hydrodynamics, so these are the three gaps are still there, nobody are did at. So I will explain broadly what they are doing is what you can do is, so I did completely on uniform sediment bed. I'm saying second one first. So uniform sediment bed I did. Now the same experimentation you can carry on the non-uniform sediment. Means non-uniform means it's a mixing of different sediment sizes. I did a D50 value 0.5 mm. So you can do a mixture of sediment and keep the same peer sizes and do the analysis and publish it. So that is one of the research gap. And another one is quantification of the stochastic nature. Means the frequency analysis I didn't did. So many spectral analysis are still how to what is the size of the eddies, everything we can understand with the help of this eddy sizes. So Taylor macro scale is very important concept. That part I didn't touch. So that is one of the gap, I can say. And another one is, okay, the problem is identified. Then what is the solution for that? The solution is designing the countermeasures. Means to stop this cover, what we can do? Either we can do any riprap arrangement or any big boulders we can keep around the pier, aggregates we can keep. What we have to do? So ultimately we need to reduce the scour around the pier. So to reduce that, what is the countermeasure techniques to reduce that? So that is also one of the scope in this area. So with this, I will stop my presentations. Now it will followed by a small quiz, and okay. So I will share the feedback, feedback as well. So after that, you can give your quiz. Okay. Yeah. So during my presentation, if you have any doubts, please let me know, and feel free to ask me. I will share my incentives in this.